bring you that. Nick and Ben are going to come up here and talk about some of the work that they're doing in advanced architectural fabrication. So we've got these two innovators who are coming, Nick being a research fellow at RMIT, and an architect who's really working kind of the forefront of advanced fabrication for architecture, and Ben, who is a structural engineer at Arup and is behind a lot of the innovations that we expect from a world-class firm like Arup. So welcome up here, guys. Give him a hand, please.
Thanks, Jordan. Yeah. So we're here today to talk about a large-scale design problem in high-end building structures. This has near-future application for 3D printed steels. So the design problem at question is this recent project that we completed in Singapore. This is Sports Hub. It's a $1 billion stadium. Features a really long-span roof. And these lightweight, long-span structures, they're extremely sensitive to self-weight. And so what we're looking at today is a potential way to reduce the weight of some of these connections. So to give you a sense of scale, this is 1,000 foot in diameter, so largest in the world. And to span that type of distance, you need to use 2D curvature to reduce the out-of-plane loads. And so to form this, you use tubular members that trace out the principal stress lines on the grid. This is all some technical stuff, but it basically creates really, really complex connections that pose some really, really distinct challenges for construction. So when we're building this, we have to build a lot of the connections between these tubular members on site at height. You have large numbers of workers. We had 1,000 on this project or so at the peak. Out on scaffolding, climbing amongst. It's dangerous, complex, hard. Current state-of-the-art best solutions for this is to use something like a big can connection. So what this is you basically have a really, really thick member that kind of resembles a Civil era cannon or something, and really, really complex cuts, something that maybe Bruce Beasley would be appreciative of. But to give you a sense of some of the geometries that we're looking at, so first of all, this one is just a very simple one. About half the 8,000 members are like this. In the middle, there's a slightly more complex one, and the most complex ones have like 12 members connecting at a single node. So to form this with a simple can connection, you can't have an efficient load path. So the engineers back in the day, like famous engineers like Peter Rice, they solved this problem with complex connections by using like cast nodes. You can form really efficient geometries. You're not limited by sphere or cylinders and plates. You can do whatever you want. Whatever's the most efficient way to get the load from one point to another through the connection. So with this, maybe the future is 3D printing of this. If it can scale up to something that can maybe be meter by meter by meter, it could be practical for an application like this, which maybe is not too far in the future. So the reason why lightweight long-span structures are an interesting application for this is that they're really uniquely sensitive to self-weight, something along the lines of aerospace and automotive problems. Span, you pay a huge cost premium with the, or you pay a lot more, you have a lot more steel per meter squared with increasing span. So it's really sensitive to the loads and stuff on it. Of those loads though, about 50% of that or more is the self-weight. Connections are maybe 20% of the self-weight. So what we're looking at is Sports Hub. We already started looking at all sorts of computational optimization. So we're already using these kind of automated workflows to design these 8,000 nodes. We want to take that dot up there in the lower right-hand corner and drop it down a little bit. If we can do that and save 10% in the materials, like this will have really, really good cost savings and implications throughout the design process. So for this project, the concept was looking at this, taking the really complex bits of the connection, condensing that down into this 3D printed bit, which makes it really simple to then make easy splices to the actual members. And with that, we're looking at some interesting ways to take advantage of 3D printing processes using evolutionary topology optimization. So I'm going to hand off to Nick to give a little bit more detail about this and the two stages of the project.
Sure, thanks. So I'll quickly just a word about the evolution of this project. The genesis, we were approached by Arup around a new initiative we had at RMIT I've certainly come across this project, this problem in practice before. And together with that, we got another young architect, an old colleague of mine from London, Christoph Kroller, who's now based in Hong Kong. And we put together a little design team through the university to start to tackle this at a couple of scales. Scale is something that hasn't been spoken about so much around 3D printing here. I think it's something that sort of used to be. So there's these issues of scales that we're working at to kind of do some quick prototyping. And as well, I think Les just hit the nail on the head. So how do we focus the customization? So how do we just focus on these nodes to have broader benefits? So at the one scale, there's this pavilion, and I'm sure there's some architects in the audience, and you'll sort of know the history of the pavilion as a sort of site for experimentation for architects. What we try to do in the little projects I do at RMIT, the research projects, are to kind of build little integrated workflows. So all these silo problems, try to break those down, make little software workflows, basically. You know, architects coming out of school these days, we actually program and we use a whole series of parametric tools and things. So what we're able to do typically is design, get feedback from some sort of analysis, here being structural, start to prototype and fabricate and feed that back again and start to iterate really quickly. And then at some point step back a little bit and say, okay, where have we got to in, you know, after 8 months, where have we got to in a certain stage of the process? How do we tackle the next phase? So just quickly, these are just a series of images of some of the iterations that happened, you know, between a little team based in Hong Kong, Singapore, New Zealand, and Melbourne, starting to tackle a series of issues at an architectural scale. So we're looking at what sort of freedom of form, architectural form for want of a better word, we can get by just simply customizing these nodes. So the system is very simple. The nodes are unique, but the members between are straight, untwisted, and we also had this ambition for the panels to be planar. So these are some of these sort of screen grabs of us grappling with these issues. This is the scheme we went with, you'll sort of see outside. And just to sort of pick up those fabrication issues, I think there are 3 critical, very pragmatic things. One being sort of how long and short those members are, what angles they start to meet together at so we actually can put this thing together. And thirdly, an ambition we had to make as much of the sort of panels, the panelization of this, planar. And in that area we spent 90% of our time and failed so far. There's a number of different research groups globally looking at this, certainly from an architectural architectural geometry perspective, and we're all kind of getting to a point where we can do synclastic sort of dome-like surfaces and anticlastic surfaces. These saddles start to become a problem. So we quickly integrate some of the feedback from Arab, some of the structural feedback, little visualizations, and then this gives you a bit of a sketch of the entire workflow. So Christoph, who's the architect, playing the architect in this role, has a little sketching interface where he can literally sketch out a topology and then use some of the free little dynamic relaxation tools to just sort of relax a shell form. We then start to analyze that structurally and do some sort of local manipulation of the form. And then we get our architectural form, and we get these node geometries and load cases that we can start to deal with. So that's the sort of the linear version of the workflow, if you like. And this is after sort of a number of back and forths and trying to work out what would be an appropriately sort of challenging but doable first pavilion prototype to do at a scale of 1 to 5. So a big enough scale that we can make and starts to give a bit of an idea of space, but small enough to be affordable at this stage. And so here are some images of that prototype. So basically at this scale, at 1 to 5, we have a whole series of workflow issues and limitations. So these are all FDM printed. So this is the printer that the architecture school has, right? We have these, and I can access these 24 hours a day. So these are all topology optimized using a fairly light optimization process. So the workflow for this is actually entirely through Rhino and Grasshopper, as most architects are using these days. So we start to do a sort of little 5-minute optimization. We start to look at the topology and start to express this difference at this scale quickly. And then everything out from that, the connections, the beams, they're all standardized. These are literally 2x4s cut down that all sort of standardized. The weakest points, the things that break first, are actually these little connection plates, so that the assembly is manageable, and we've got these are standardized plates, we can just replace them. So we've focused the customization on these nodes. So just a couple of images, but I'd encourage you to go and have a look outside if you haven't already. So this gives you an idea in this setup, a single layer shell, the types of connections we have. We have single and double beams coming together where we touch the ground, and we have 3, 4, and 5 members coming together sort of through the shell structure itself. So these start to give us these nodes we can start to focus on as a group. So in parallel to the pavilion prototype, we also work up the full-scale metal nodes. And this is in the spirit, just sort of briefly, and I'm sure all of you here are sort of quite across this, in the spirit that this additive manufacturing is moving from a prototyping phase to a phase that can very readily make finished parts. This is less of a linear workflow, of course. This is genuinely a bunch of people sitting around a table, sitting around a Skype connection, talking about one thing and going back and forth a lot. So just to quickly touch on Christoph Kroloff and his little practice lead, we've got a structural optimization group led by Professor Mike Shee, myself and the team at Spatial Information Architecture Laboratory at RMIT, this research group. So we're architects, but we look at workflows and a whole series of environmental issues. We have Arup talking about a whole series of real-world issues driving, and also the structural engineering. And we have an additive manufacture group that sort of starts to plug in input about the metal selective laser melting machine they have. Oop.
Yes, and so just a bit about the kind of generative design of these nodes. So this is a process called bidirectional evolutionary structural optimization. So the principle is you have a bunch of brick elements in a 3D model. You apply loads as to the free body structural model, and it iteratively runs linear analysis across a whole bunch of load cases. It's quite key when you're doing optimized things like this. Usually we just consider the worst 1 or 2 load cases. With this, since we're really refining it down, you have to consider a much wider range of load cases to make sure you cover all the kind of maybe not critical, but still very, very important load cases. And so it just basically runs iterative analysis, defines which brick elements are working hard, which ones are not, and either adds or subtracts elements as needed until it converges to a rather efficient shape.
So just to give you an idea of the resolution as well, this starts with a slightly more than 500,000 voxel animation. The plastic ones were about 60,000, so there's a major speed difference. This takes about 2.5 days, this optimization process at the moment. But there are algorithms that have been, we talked about algorithms designing things and generative design, etc. These algorithms have been in development for 20 years now and are still being, the hardware's catching up and the systems are catching up. So this is a little test case I thought I'd take you through. It's a series of bending loads plugged in, one of the early ones we did. So you can see that the point on the right here is fixed, and then we have uniform bending loads applied from each side. And this is the form that's generated through the algorithm. And that was then analyzed for certain issues around printability. On the left here, there's an early prototype printed in aluminium on the printer at RMIT. Here we've worked very hard to get the support structure down to an absolute minimum. You see on the right a couple of early versions where we had a whole series of problems. The FDM process is different to, the FDM process and the laser melting process are different in the one that's actually providing support for gravity and the other's transferring heat. So they're quite some technical issues still. And I think there's a lot more work to do on this support structure optimization, and certainly bringing that into the algorithm. So here are some little early just sketches done with Autodesk Mesh Mixer, which I'm sure some of you are familiar with. And then the prints don't always work. Here's an overheating failure on an early part. We're in the thick of the research here. So what we did was to take 3 load cases, one with where 3 beams come together, one with 4 beams coming together, one with 5, apply the actual axial shear and bending loads across those nodes, and let these algorithms develop the forms and start to look at the printing process itself. And then there are 2 of these metal nodes that we've prototyped so far. So these are 220 mil, so about 8 inches across. They're also out in the main hall. So go and have a look. These are printed in stainless steel as the first pass, which certainly is one option we have for the materials, and there's a lot of discussion about which material's really the most appropriate. So this is with 4 points coming together, and actually oriented here in the position it is in the 3D structure. So you really don't have a base point to start to print this off or build this off, so a series of issues. And here's the element that's 3 beams coming together. And so these forms are quite, these forms sort of give back a whole series of layers of design beauty, ugliness, design intelligence themselves. And certainly, as a number of speakers have picked up on, aren't designed by a person, but through a sort of complex iterative process. So I think there are other versions where we might actually add a layer of design back on top of this. Let's say, so these 2 are out in the main hall. So quickly, just to wrap up, a couple of research questions as they present themselves. I mean, the very next immediate step, those who printed just at Christmas, is to actually break those nodes, see how they go in the structural testing. Start to look at the material properties, how weldable are the printed parts, and then start to look at the optimization algorithms further. How do we incorporate buckling, specifically Ben's been asking about. How do we improve those optimization techniques to start to think about additive manufacture within that optimization process a bit more than just volume and topology optimization? We don't have a base point necessarily, so it's some challenges there. And I think importantly, when you start to have a whole series of customized parts, can we start to then sort of bottom up in a bottom-up product family kind of way, group those parts into types so that we can preempt certain manufacturing issues that are going to come up. So while the geometries are going to be unique, we can pick little families of similar types and start to preempt some of these problems.
Yeah, and so I think this technology has huge promise, and we've really been encouraged by this. And while 3D printing steel is rather expensive still for construction industry type applications, I think one important point to consider is that the cost of a connection on site, a relatively small portion of that's actual materials and printing and fabrication. I mean, just reducing the weld complexity and making it simpler to build saves a tremendous amount, and we would see that even in place in like Singapore, where labor is relatively cheap. In the US, I mean, this could have tremendous applications in the near future. So we're looking to incorporate what we've learned in this project on large span roofs in the near future. So hopefully in a few years' time, you'll see some of these going up, and we'll be excited. See how it turns out. Thank you.